Welcome back to EET1015C. This is Fundamentals of DC Circuits. And in this lecture, we are going to be studying the branch current, loop current, and node voltage methods. And in a nutshell, we're going to be figuring out the best way to apply those methods based on the circuit that you're given. So in the next problem, we're going to determine the best approach between the branch current, loop current, or the node voltage method to find a solution. And what we're going to do is consider which method might be the most efficient or which method is going to be best to determine what we're trying to find. For example, if you're trying to solve for a current, branch current and loop current methods might be more direct. If you need a voltage from a particular point, node voltage might be more appropriate. At the end of the day, we want to consider things like the number of variables that are going to be involved with each method. Remember that the more variables you have, the more complex your equations become. Think about the type of circuit you have and what you're trying to find. Once you have selected an approach, we're going to solve the problem. If your approach becomes too complicated, you might consider selecting a different one. So here's the first problem. Currently, there is no load connected to terminals A and B in the circuit below. What I would like for you to do is to pause this video right now and try to solve this particular circuit. We want to find the voltage across R3. Think about the branch current method, the loop current method, and the node voltage method. Pick one, pick whatever one you feel would be the best one or the most applicable one, and solve for the voltage across R3. When you're done, come back to the video and I'm going to show you the solutions for each method. Then you can compare and contrast to see which method was the most efficient. And sometimes there is no method that is the most efficient. It all depends on your circuit and what you're trying to find. But we are going to go through each individual method, look at the differences between all three, and also you'll be able to check your work when you're done. So here's the first approach using the branch current method. Remember, our end goal is to find the voltage across R3. In order to do that, we need to find the current going through R3. And we're going to start by using the branch current method to find the current through R3. So remember that when you begin the branch current method, you have to assign a current to each branch. So we have I1, I2, and I3. After you assign your currents, you're going to assign a polarity to each resistor. That polarity is based on the flow of current through that resistor. Remember, the positive terminal is where current enters, the negative terminal is where current exits. So now on my diagram, you can see that I have labeled each branch current as well as each polarity for each resistor. Next, we're going to do a KVL around each closed loop in the circuit. There are two closed loops. One loop begins with the 8-volt source and goes around this way. The second loop is inside the diamond shape right here. So we're going to begin with a KVL around the left loop. If you start, let me get my pointer. If you start from right here and go around the loop clockwise, you'd have an equation VR1 plus VR2 plus VR4 minus 8 volts equals 0. Next, we're going to take this equation and we're going to replace every voltage drop with a current multiplied times a resistance. So VR1 is going to be the current through R1 times the value of R1. So that'll give you 10 times I1. And then for VR2 and VR4, since these two resistors are in series, we can combine these two resistances together. 4.7 plus 2.2 gives you 6.9. So we're going to combine those together and multiply that by I2. Once you simplify, there's your first equation. Keep in mind with this method, we initially identified three things we don't know: I1, I2, and I3. So remember, you need three equations in order to relate them all together and solve for each unknown using a matrix or algebra. So our second equation is going to come from doing a KVL around the right loop. If you start right here and go around the loop counterclockwise, that would give you an equation of VR2 plus VR4 minus VR5 minus VR3 equals 0. Remember, when you're doing your KVL, you can start from any point along the path and you can go in any direction. As long as you follow the polarities of your resistors, your equation will be correct. Now we're going to replace each voltage in our equation with its Ohm's law equivalent. Remember, voltage is current times resistance. So we're going to replace VR2, VR4, VR5, and VR3 with a current times the resistance. Once again, R2 and R4 are in series, so we can combine them. And then we can say that the voltage across these two resistors combined is going to be 4.7 plus 2.2 times I2, which flows through them this way. We can do the same thing for R3 and R5. They're in series. We can combine them. And then we're going to say that the current going through both of these is I3. So we have 3.9 plus 8.2 times I3. Keep in mind that we identified I3 to be flowing down this way, but because of our KVL going the opposite way, it opposes the direction of I3. That's why this is a minus sign right here, because the voltage we're calculating is actually opposing the direction that we initially picked for I3. If you follow your original KVL equation, exactly as it was written here, and plug in your values for each voltage, this is the equation that you'll get. Simplified, you'll get this equation right here. And this equation is super convenient because it gives me I2 in terms of I3. This will help me to eventually eliminate a variable. So we have two equations right now. We need a total of 3 equations to match with our 3 unknowns. Our third equation will come from a KCL at the node, which is right here. And we can see that I1 is equal to I2 plus I3. Now that we have 3 equations for our 3 unknowns, we can use a matrix or algebra to solve this circuit to find our unknown values. I'm going to continue showing you how to solve this algebraically. So I'm going to take equation 2 and plug that into equation 3. I'll go back just to review. Equation 2 is right here. Equation 3 is right here. We're going to plug equation 2 into equation 3. So we get that I1 is equal to 1.75 I3 plus I3. Or if you combine those, that gives you 2.75 I3. I'm going to call that a new equation, equation 4. Now I'm going to take equation 2 and equation 4 and plug them into equation 1. I'll quickly go back. Equation 2 is right here. Equation 4 we just solved for. We're going to take both of those and plug that into equation 1. When we make those substitution, here's what equation 1 becomes. Notice that the whole purpose of these different substitutions is to create an equation where I only have one thing I don't know. I only need to find I3 in this equation. So I can solve this particular equation for I3. Once you find I3, you can use that to find I1 and I2 by plugging into your previous equations. So for example, I know I1 is equal to 2.75 times I3. Take I3, plug that into this equation, and you have I1. And you can do the same thing for I2 by using equation 2. So now that I have my 3 branch currents, they all came out to be positive values, which means that the direction I initially picked for each current is correct. I now know the current through R3, which means I can go find the voltage across R3. And I end up with 1.66 volts. That's how you would solve this problem using the branch current method. Keep in mind, with this method, we had 3 unknowns, so we had to have 3 equations, and we had to know how to solve for those 3 unknowns. You can use a 3x3 matrix, or you can use algebra. Next, we're going to do the same problem with the loop current method. So to begin the loop current method, you need to start by identifying your loop currents and labeling them. So we're going to have IA and IB. Then we're going to assign polarity to each resistor the same way as before. Keep in mind that if you have a resistor where you have two currents flowing through it, like R2 and R4, IA is going to flow through R2 this way. It's going to flow through going down. IB is going to flow through going up. Going up. So the polarities are labeled on either side to reflect that we have two opposing currents. When we write our equations, if we're writing our equation from the point of view of loop A, we're going to use this polarity. When we write our equation from the point of view of loop B, we'll use this polarity on the inside. Remember that if one current is going down while another is going up through that particular resistor, we have to subtract the two loop currents to find the total current going through that particular resistor. So we've identified our loops, and we're going to do a KVL. The same KVL equations that we did for a branch current method will apply here. The difference is when you start rearranging these voltages to be in terms of a current times a resistance, now we have a loop current instead of a branch current. That's going to change the way our equations look. But keep in mind, I only have two things I don't know, IA and IB. So I only need two equations to relate them instead of needing three for the branch current method. So take the KVL for the left loop. Again, it's the same equation we've already derived from before, but now we're going to plug in our loop currents. The voltage for R1 is going to be 10 times IA. The voltage for R2 and R4, again, these are in series. We can combine those together, and then the current that's running through this branch is going to be IA, going down, minus IB, which goes up. Simplify this equation, and you have your first equation showing a relationship between IA and IB. Next, we're going to do KVL for the right loop. Again, we're going to pick a point on the loop and go around the circle. In this case, I picked this this point right here and traveled clockwise around the loop. I picked this point and I picked that direction simply to mimic the flow of IB, which has already been identified. So if I start here and travel around the loop clockwise, my KVL equation becomes VR3 plus VR5 plus VR4 plus VR2. Remember, I'm following the polarities on the inside of the loop. Now we're going to replace each voltage with a current times a resistance. We know that R3 and R5 are in series. We can combine those together. 8.2 plus 3.9 gives you 12.1 ohms. That resistance is going to be multiplied by IB flowing through it. And then we have R4 and R2, which are also in series. Combine them together, and that resistance is going to be multiplied by IB minus IA because they are in opposing directions. Simplify, and you have your second equation. Now we're going to take these two equations and use algebra to find IA and IB. You can use a matrix, or you can use the fact that IA is already written in terms of IB. We can take IA and plug this value into equation 1, and then we can solve that for IB. So we're going to do that right here. We're going to take equation 1, plug in our equivalent value for IA, and solve this for IB. Once you have IB, you can take this value, plug it right back into equation 2, get IA. Since our values came out to be positive, the directions that we picked for IB and IA are correct. We know that the current for R3 is the same as the current for IB. Since the direction for IB was correct, we know the current through R3 is going down, and we know its value, 201.89 milliamps. We know that the current for IA is the correct direction, and the current through R1 is IA. Therefore, the current through R1 has to be traveling to the right. Then we could take the difference between IA and IB to find the amount of current that flows through this path where you see R2 and R4 connected in series. When you take the difference, you're going to look at whichever one is bigger. IA is bigger than IB, which means the direction of IA is the final direction for your final answer. So you do 555.8 milliamps minus the 201.89 milliamps. And we know that since IA is the bigger current, its direction wins. And so the direction of the current flowing through R2 is going to be down because IA would have been flowing down through R2. And of course, we know that's also the current for R4. So we found each loop current. You can easily translate that to a branch current. Notice our answers are almost identical to the solution using the branch current method. And then we can take the current for R3 to find the voltage for R3, and you get the exact same answer, 1.66 volts. And that's how you solve this using the loop current method. Notice we had two equations for our two unknowns. It was slightly easier to solve than having 3 equations and 3 unknowns. Lastly, we're going to solve this using the node voltage method. In order to solve this using node voltage, you have to start by assigning a branch current. There's our 3 branch currents and polarities for each resistor. We're also going to identify a node for which we can calculate the voltage. In this case, our node is going to be right here, node X. I just used X because A and B are already labeled on the picture. A and B are the points where we might connect a load. So since those are already labeled as potential points, we're not going to use A or B, we're going to use another letter, so I used X. Now that we've identified each branch current, we need to write an equation for each current on the picture in terms of a voltage drop divided by a resistance along that path. So for example, I1 is going to be equal to the voltage drop from this point to this point divided by the resistance along that path. So in that case, we have a voltage of positive 8 volts minus the voltage at node X, that's our voltage drop along this path, divided by 10 ohms, that's the resistance along this path. We're also going to write an equation for I2. I2 begins at node X, so we're going to have the voltage at node X, and I2 ends at ground, so we have Vx minus 0, divided by the resistance along this path, so we're going to combine R2 and R4 to get 6.9 ohms. And we're also going to do the same thing for I3. I3 begins at node X and ends at ground, so we have Vx divided by the resistance along this path. Now that we have our 3 equations for each current in terms of a voltage divided by a resistance, we're going to do a KCL at the node. We know that I1 has to be equal to I2 plus I3. Now we're going to substitute each equation for I1, I2, and I3 into our KCL equation. And now we have one equation with one thing we don't know, Vx. So we just need to solve this one equation. You will remember from the node voltage video that we're going to solve an equation with fractions like this by multiplying by a common denominator. If you need review on how to do that, please go back and watch the node voltage video. It will explain this concept in detail. So since that's already covered in another video, I'm not going to go over it in detail here, but I'm going to continue by multiplying by a common denominator to get rid of all the fractions and simplifying. Once I simplify this equation, I can combine like terms, use some algebra, solve for Vx. Vx comes out to be 2.44 volts. Now that I have Vx, I can take Vx and plug that right back in to each equation up here to find each branch current. And you'll end up with I1 being 555, I2 being 354, and I3 being 202 milliamps. Now that I have all 3 branch currents, notice I put the direction for each just confirming that the initial assumption for what was chosen is correct because all our answers came out to be positive. Now I can take those branch currents and I can find any voltage I want within the circuit. In this case, the goal was to find VR3. Once again, you'll see that VR3 comes out to be the same value. So this is how we can use branch current, loop current, or node voltage to solve a particular problem. The method you choose is ultimately up to you, but you want to think about what you're trying to find and what might be the most efficient way to find it. In general, the less equations that you have, the easier it is for you to solve the problem. So node voltage comes out to be the simplest because you only have one node, which means you only have one unknown, which means you only have one equation that you have to solve. However, a pitfall of node voltage is that it is sometimes harder to understand how to set up these initial equations for each branch current. So you have to make sure you really understand that first step of setting up these three equations for each current in terms of a voltage before you start to apply the node voltage method. If you can set those up correctly, node voltage is usually simpler because it has less unknowns. All right, so we're going to do another example where we compare all three methods. Look at the circuit below. Notice that you have several sources, a 9-volt source, 4.5-volt source, a 15-volt source. Notice the polarities of each source. And then we have a ladder network of resistors. We're going to start by looking at this problem, and we're going to try to solve for every current in each branch. And we're going to start by using the branch current method to do that. So we're going to write the branch equations and take a look at what we get. So if I'm going to use the branch current method to solve this circuit, I'm going to assign a current to each branch. And then I have to do a KVL around each closed loop. Notice I have 3 closed loops, so I have to do 3 KVL equations. Now I don't have the polarities shown on this particular problem. I'm leaving it up to you to make sure you know how to label polarities correctly. So on your paper, as you're doing this problem, make sure that you are labeling the polarities. So for the left loop, here's my KVL. If I start right here and go around the loop clockwise, that's the equation you'll get. VR1 plus VR2 minus 9 equals 0. Then I can simplify this equation by plugging in values for VR1 and VR2. That gives me my first equation. Next, I'm going to do a KVL around the middle loop. I'm going to start right here and go clockwise around the loop. So you're going to have a minus VR2. Look at the polarity of I2. Look at the direction you're going. So this is going to be plus, minus, for example. So we have a negative voltage here if we're going this way around the loop. Negative VR2 plus VR3 plus VR4 minus 4.5. Notice the polarity of that voltage source right there. You hit the minus sign first. So you're going to have to make sure you reflect that in your equation. Look at the minus sign right there. So there's our equation for the middle loop. We're going to make our substitutions for each voltage drop. And that's our second equation. Our third equation is going to be a KVL around the right loop. I began right here and went around clockwise. Notice once again, you hit the minus sign of this 15 volts. The polarity is flipped from how we normally see it. We normally see it like this, but the minus sign is on top. If you go around this way, you hit a minus sign first, so make sure that your KVL equation reflects that. Once you simplify, there's your third equation. Now we have 5 things that we don't know, and we only have 3 equations so far. You need 2 more equations, and those 2 other equations are going to come from a KCL at node A and a KCL at node B. So there's equation 4 and equation 5. At this point, if you haven't realized it by now, you should start to realize that this is becoming far more complex than any circuit we've done so far. We have 5 equations, we have 5 things we don't know, and we have not discussed how to solve this using a matrix that large or using algebra with that many variables. So it is not really recommended to continue down this particular path. Branch current will work, it's just very complicated to solve when you have 5 equations and 5 unknowns. So we're going to stop right here. We're going to back up and we're going to try another method to see if it will be simpler to find what we need to find. So now we're going to use the loop current method on the exact same circuit and look at the differences. Here's my 3 loops, IA, IB, and IC. I'm going to do a KVL around each loop just like I did before. As I plug in my values for VR1 and VR2, I'm going to make a point here of pointing out something important. If you look at the equation for the KVL, I wrote 56 IA plus 27 IA minus IB equals 9. Notice that the label on the resistor is 56K. I didn't write the K. I didn't write 56,000 times IA. I wrote just 56. You can do this. This is fine. It makes your algebra simpler as you're working through the loop current method on this problem. There's just one thing you have to remember. If you eliminate your 56,000, if you turned it into a 56, when you calculate all your answers, they're automatically going to be milliamps because you started with everything in kilo ohms. So you have to remember that anything that comes out of your calculator as a final answer is already in milliamps. So let's just say, as an example, if you are calculating the value for IA and you get down to the very last point of this problem and you plug and chug your values and your calculator gives you a number like 80 times 10 to the negative third, that's 80 times 10 to the negative third milliamps. It's already in milliamps. That exponent of 10 to the negative third is going to be applied to milliamps, making your final value actually microamps. So that's an important thing to remember when you start doing these problems. If you decide to chop off the K and just use the digits shown in the picture without reflecting the units, that's fine, but you have to remember what you're starting with. You're starting with everything in kilo ohms, which means by default, everything is going to come out automatically as milliamps. So if you have an exponent like this in your answer, you have to apply that to a unit of milliamps. So that's an important point I want to make because that's going to be important later in our problem. But now we can continue with our KVLs. So here's our KVL around the left loop. Simplify it, and that's your first equation. Here's the KVL around the middle loop. This time, my KVL follows the direction of IB. It's following the direction of IB. So we have a plus VR2 plus VR3 plus VR4 minus 4.5 equals 0. I'm going to fill in. Notice that the voltage for R2 is going to be IAB minus IA because they flow in opposing directions. Notice that the voltage for R4 is going to be 33 times IB, which goes down, minus IC, which goes up, opposing directions. So we subtract them. If those two loop currents happen to be the same direction, you would just add them instead of subtracting them. Simplify, and you have equation 2. Then I'm going to do a KVL around the right loop, starting here and following the direction of IC. And we're going to plug in our values for VR5 and VR4. Notice that VR4 is now 33 times IC minus IB because this is our point of view. The loop current for your point of view comes first. That's why VR4 is written this way in this equation, but it's written this way in this equation. You have to pay attention to point of view. Simplify that equation, and now we have our third equation. And now we're going to solve this either using algebra or a 3x3 matrix. Here's the algebraic solution. We're going to take equation 1 and write it in terms of IA. So I'll go back to equation 1. Equation 1 is right here. I'm going to solve that for IA. I'm also going to take equation 3 and solve that for IC. Why did I do that? Because I have IA in terms of IB. I have IC in terms of IB. If I take this equation and this equation and plug those in to equation number 2, I can eliminate the IA there. I can eliminate the IC there, and I have one equation with one thing I don't know. I can solve for IB. So I'm going to plug these values for IA and IC into equation 2. Now it's a pretty long equation, but it just has one variable that you don't know, so you can use algebra to solve this equation for IB. You're going to get 78.48. Now, when you do this in your calculator, you're going to get 78.48 times 10 to the negative 3. Remember, that really corresponds to 78.48 milliamps times 10 to the negative 3. When you write your final answer, and only when you write your final answer, will you convert it to microamps. So our final answer is 78.48 micro. When you take this value and plug it back in up here to find IC, and plug it back in here to find IB, you are just going to write 78.48 times 10 to the negative 3. You're not going to convert it to micro. You only convert to micro for the very final answer. That's it. So you're going to take the value for IB. You're going to take the value your calculator gave you, which is 78.48 times 10 to the negative 3. That's what you're going to plug in right here to find IC. You're going to plug it in right here to find IA. Both of those values will also come out with an exponent of times 10 to the negative 3. Both of those values are already milliamps by default. You'll apply the exponent of 10 to the negative 3, and you'll get micro as well. So there's our final answer for IA, IB, and IC. Now that you have each loop current, you could easily convert that to each branch current. We know the current through R1 has to be the same as IA. We know the current through R2 is going to be the difference between IA and IB, and whichever one is bigger, that direction wins. IA is bigger than IB, and IA goes down through R2. So the direction of I2 is down. We know I3 has to be the same as IB. We know I4 has to be the difference between IB and IC. IC is bigger and IC flows up. IC flows up through R4. And then I5 has to be the same as IC. So branch current method was really not the best approach for solving this. Loop current was fairly reasonable. We had to solve for 3 unknowns, but it wasn't too difficult. And again, you could have also used a 3x3 matrix to solve this. But there's the algebra. So now we're going to do the same problem one more time using node voltage. We're going to solve for the voltage at nodes A and B. We're going to use those 2 voltages to find the current through each resistor. There are the branch currents. We have to write an equation for each one of these currents in terms of a voltage drop divided by a resistance along that path. I1 is going to be 9 volts because we have 9 volts here, minus the voltage at point A divided by 56. I2 is going to be VA minus nothing divided by 27. I3 is going to be VA minus VB divided by 91. I4 is going to be VB minus negative 4.5. You got a double negative there, so that's going to come out to be positive. Same thing with I5. We have VB minus a negative 15 divided by 82. So we've got our 3 equations. And then what we need to do is a KCL at node A, a KCL at node B, and we're going to replace each branch current with one of these values. So we can see that for node A, I1 has to be equal to I2 plus I3. We're going to replace I1, I2, and I3 with our values here. Simplify to get an equation, equation 1. Remember, go back to the node voltage video if you're not understanding the steps I'm taking here. It's explained in detail in that video. Now we're going to do a KCL at node B. We can see that I3 has to be equal to I4 plus I5. We're going to plug in our values for I3, I4, and I5 and simplify. Now I have two equations with two unknowns. I'm going to use a matrix to solve this. Here's my two equations. There are my coefficients. There's my characteristic determinant. And here's how I'm going to solve for VA and VB. So we end up with VA being 1.49 volts. We end up with VB being negative 5.66 volts. There's nothing wrong with a negative sign. That just means that the current flowing out of VB flows the opposite way than what you picked. We're going to see that R4 is actually going to have a current going up instead of down. So take VA and take VB, plug those values into each one of these equations, and then you'll have the current in every branch. Do not change the negative sign of VB. So when you plug VB in right here, you're plugging in a negative 5.66 minus negative 15. When you plug it in right here, same thing. The negative sign goes with you. Assuming you have done everything else right until this point, there's nothing wrong with having a negative sign right here. And do not omit it when you go back and plug it in to all of your branch equations. That's very important. So when you go and plug in VA and VB into each one of these equations, here's the currents that you get. Notice that I4 came out to be negative, which means the current does not flow down as we assumed, it flows up. Do not change anything on your picture. Do not ignore the negative sign. Just write the correct direction based on what you know. I assumed it went down. I got a negative sign in my answer, so it actually flows up. That's all you need to do. Don't change anything else when it comes to your picture or your math or your work. You don't have to change anything. Just make sure that you can interpret your answer and know what the correct direction is. Also, with this approach, your answers will come out to be the exact same as they were for loop current. So again, the method is not nearly as important as understanding how to apply it. All three methods work. All three methods will give you the correct answer if you apply them correctly. Just make sure that you can understand each method, and for the purpose of saving yourself maybe a little bit of time or energy, it may be useful to look forward and figure out which one might be the fastest for me to apply. In this problem, node voltage only gave you 2 unknowns, loop current gave you 3 unknowns, and branch current gave you 5. So before you start the problem, before you pick up a particular direction, keep in mind that you want to look for those types of things. What's going to be the simplest way for me to solve this using one of these 3 methods? All right, so for our last example, we're going to sort of put everything together that we've been studying both in this particular chapter as well as throughout the semester. We're going to be using the techniques discussed for node voltage, loop current. We're also going to be using KVL, KCL, Ohm's law, etc. We're going to solve for every current in this circuit, as well as the voltage at node A, node B, and node C. Notice where ground is before we begin. Ground is in the middle here. Notice we have a voltage labeled right here. That means from this point to ground is 4.32 volts. We also have a voltage labeled here. That means from this point to ground is negative 5.25 volts. Again, this is a great point where I would really encourage you to stop the video and try to solve this on your own. You can't always learn by just watching someone else do it. Eventually, you have to try it on your own. I want you to try it on your own and see how far you get. Then when you're ready, come back and look at the solution and figure out where you might have made a mistake or where you just may have overlooked a key piece of information. Okay, so now we're going to go over the solution for this. We're going to begin with I7. We know the voltage from this point to ground is 4.32 volts. We can use Ohm's law to find the current flowing through R7. And we know it's got to flow this way. So that's just Ohm's law. So we know the current through R7. Next, we can find the voltage at node C. The voltage at node C basically means find the voltage from this point to ground. We know that from this point to ground, there is a negative 20 volts along this path and a positive 4.32 volts along the same path. So if we combine those, keeping in mind that the 20 volts is negative, we can see that the voltage from point C to ground is negative 15.7 volts. Next, we can find the current through R6. We're going to do that by doing a node voltage style application. If we were doing node voltage and we were trying to find the current along this path, we'd say that it's a voltage drop from one point to the other divided by the resistance along the path. We're going to assume that the current flows this way. You could just as easily assume that it flows the other way. All that means is if your answer comes out to be negative, you know your assumption needs to be reversed. If we assume that current flows down through R6, we could say that this current is equal to the voltage drop, which would be negative 5.2 volts at this node, minus the negative 15.7 volts we just calculated at node C. That's the voltage drop from this point to this point, divided by the resistance along the path, will give you a current. So we can find the current for I6 by using a node voltage style application of writing a current in terms of a voltage drop divided by a resistance along a path. Next, we can find I4. We can find I4 by again making an assumption. We're going to make the assumption that current flows this way. If we do a voltage drop from here to here, that would be 0 minus negative 5.25, making that positive 5.25, divided by the resistance along this path. Again, you could have just as easily decided to do the current this way as your initial assumption. Not a problem with that. Your answer just would have come out to be negative. And that still would be correct because it just reflects that your assumption was incorrect. So now we have I4, which flows into this node this way. Next, we're going to solve for I1. We're going to make an assumption for I1. We're going to assume I1 flows down. So then we know that I1 plus I4, both of those are going in, has to equal I6 coming out. So then that means that I1 has to be I6 minus I4, KCL. That's what we're doing right here at this node, KCL. So again, the assumption is arbitrary, but in this case, we get a value for I1 to be 193 microamps. Next, we're going to find the voltage at point A. We could do that one of two ways. We could find the voltage drop from here to here across R2. We don't know the current through R2 yet. The other way is to find the voltage drop along this path right here. So if we look at the path from point A around here and to ground, we can say that we would have to have the voltage drop for R1 combined with the voltage drop from this point to ground. From here to ground, the voltage has already been identified as negative 5.25 volts. So we've kind of got this piece covered. We simply need to combine that with the voltage drop seen here. We know the current through R1. That means we can find the voltage drop across R1. And we know the polarity of that voltage drop based on the direction of the current through R1. So the voltage at point A is going to be this voltage minus this voltage. Remember, this particular voltage covers this piece of the path because we know the voltage from this point to ground already. So when we combine these two voltages, you'll see that here. We're going to calculate the voltage for R1 using the current for I1. You get your voltage at node A. Next, we can use that voltage to find the current through R2. The assumption here is that current flows this way. So we have 0 minus negative 3.7, that's why it's positive, divided by 10K. There's your current for I2. Next, we're going to find the current for I5. The current for I5. The assumption is that current flows this way. So we've got one current going in, which is R7. We have 3 currents going out, which is R4, R2, and R5. So we can use KCL to figure out what I5 is because we know this current, we know this current, and we know this current. So when you use KCL, you can find the current through R5. We know it's going this way. Next, we're going to find the voltage at point B. That means the voltage from here to ground. If you look at the direction of the current going through R5, we can see that the polarity for this resistor would look like this. So if I take the voltage from point B to ground, it has to be negative. So we're going to take the current through R5 times the value of R5, and you get negative 5.58 volts. Negative again because we're starting from B and going to ground. That's what V sub B means. Start at V, go to ground. Next, we're going to find I3. The assumption is that I3 flows this way. If you think about node voltage and writing that current in terms of a voltage drop divided by resistance, it'd be VA minus VB divided by the resistance along that path. Plug in your values for VA and VB, and you'll get the current for I3. Lastly, we're going to find the current for I8. We've got R5 going this way, R3 going in, so the natural assumption would be that the current is flowing out. And we can add I3 and I5 to get that final current flowing out. So this problem is a great problem for figuring out what tools in your toolbox to pull out when, depending on what you're looking for. We used a number of different things to solve this. It may not have been the only way to solve this problem. There are other ways to apply the tools. So if you solve this on your own and you used a different methodology, as long as you got the same final answers, great job. You can use the tools in a number of ways. For example, we really didn't use KVL to solve this, and we could have. There were other ways to apply node voltage. For example, there were other ways to apply Ohm's law. So those are all options as well. But this is a great problem just sort of to sum up the semester and be able to look at a circuit like this and figure out, okay, what tool can I use to find this piece? What tool can I use to find that piece, etc. So this is a great practice problem for making sure you understand all of the tools we've been working on this semester. KVL, KCL, Ohm's law, node voltage, branch current, loop current, etc. So looking forward, be prepared to demonstrate all of these methods on the final exam. You have to know how to use branch current, loop current, node voltage, in addition to a few other things. But definitely expect that a majority of the final exam is going to ask you to apply these methods to solve a circuit. Your work on the exam must be clear, it must be easy to read, you must show each step. Answers that don't have understandable work, where it's very easy and clear to follow what you were doing and how you were applying the method, will receive little to no points. So if I can't understand what you did and if I can't understand how you got your final answer, you won't get very many points for the problem. So keep that in mind, that you will see all 3 of these methods in the final exam and that you have to demonstrate that you can apply them. So that's the end of this video. Please email me, send me a Canvas message if you're having trouble understanding these methods. We can set up a time to meet and go over anything that you need to go over so that you can be prepared and successful on the final exam. I'm here to support you in any way that I can. Just reach out to me and let me know what you need from me. And that's it for this video.